area or a watershed. And in hydrology, remember, and especially surface the surface water hydrology, or generally hydrology, the watershed is a very critical component of the of hydrology, because that is where the interactions of water occurs. And the watershed is also includes the physical framework, the physical aspect of hydrology, that is the surfaces on which water flows and so forth and so on. And those surfaces are different, and like I mentioned yesterday, they are different based on the types of soil, the types of land uses and so forth, and so the slope, all those things determine how the water flows. So if we were now to add rainfall into, I'm just literally saying, imagine where you are. We add rainfall, and then we say we are going to account for all processes, so that we account for all components of the hydrologic cycle. Excuse me. It is rather a little bit complex. It is rather a little bit complex. So normally, sometimes in a very basic way of analyzing the hydrologic continuum, or the hydrologic landscape, in very simple terms, and sometimes we imagine the hydrologic landscape as a system. And in this system, it will have inflows into the system, and outflows into the system. And then inside the system itself, so into the system we have inflows into the system, and then we also have outflows. Outflows from the system. And then inside the system we have processes. What are some of these processes? We have infiltration, we have water storage through moisture content, we have groundwater flow, we have overland flow, and so forth and so on. These processes, not processes. So such kind of a systems concept is one of the ways of simplifying the hydrologic spectrum, the hydrologic framework. And at this level, most of the things that we are actually going to be doing, most of the things that we are doing we are just going to follow the systems concept, whereby, we know the inflows into the system, and in hydrology, most of the inflows are rainfall, and we know the outflows from the system. But now we lump together all the processes. We really do not want to know the nitty-gritties of what happens, so that the outflows are generated. If you recall from engineering hydrology 1A, if you did the rainfall runoff, generation of rainfall or generation of excess rainfall, and if you didn't, you can tell me so that I don't use examples that we have not done. If we remember generation of excess rainfall, there are a number of ways for example, the runoff coefficient method, whereby we have rainfall, then we lump together all processes through the runoff coefficient, and the runoff coefficient is usually a fraction off is usually a fraction is between 0 and 1, and the outflow is the excess rainfall that generates overland flow. So that is a basic example of a systems concept. Why do I introduce it? I have already said it is going to be, we are going to apply it everywhere, almost everywhere, in what we are going to tackle, apart from the probability part. When we go back to the course outline, the hydrologic flow routing is also, kind of a lumped system, a systems concept. The hydraulic flow routing is based on physical principles, and it is a little bit much more complex. And like I said, we will not be dealing with it in this course. Yeah, so another thing I want to say is I've not yet made slides for this course, so we'll just follow the notes as they are and try to simplify them as much as I can. Normally, from engineering hydrology 1, we know all these components of the hydrologic cycle, and these components can be grouped into 3 subsystems. We have the atmospheric water that where we have precipitation, evaporation and transpiration, and interception also occurs at this stage. And then we have surface water. Then we have subsurface water. Surface water, things to do with overland flow, surface runoff, and overland flow, surface runoff, and runoff to streams and oceans. Or basically, it is runoff. Basically, it is those two: overland flow and surface runoff. And we have then the subsurface water. Things to do with infiltration, subsurface flow. When I'm talking about subsurface flow, we are talking about flow in the unsaturated zone. When infiltration is happening, there's usually a flow of water, a little bit complex because, it is flow of water in a situation whereby the pores are saturated. Then we have groundwater recharge. Wow. I'm requesting you bear with me, but we have to do. So then we have groundwater recharge through percolation, and of course we have the groundwater flow. Remember, sometimes the groundwater flow at the point where, for example, the groundwater in the shallow aquifer meets groundwater surface, we have springs, and in that situation, we have springs, and then in that situation, then the water joins surface water. The water joins surface water. So all this, this hydrologic cycle, when you look at it and the way we have done it, we have created 3 systems: an atmospheric water system, surface water system, and a subsurface water system, and all of them are interconnected between water, because water comes from one of the system to another. And again, you can look at the hydrologic cycle as a whole, as a system. Because of the complexity, and when you in the outside there in the field, when we are doing solving hydrologic problems, sometimes you find that you do not need to really include, because of the complexity of this system, you do not need to include all these components of the hydrologic cycle in your analysis. And most of the time, it is very common that only a few processes are considered at a time. For example, if we want, for example, like what I said, if we want to calculate excess rainfall, we only need to know the precipitation, We need to know maybe the interception, we need to know infiltration, so that we can calculate excess rainfall. We don't really need to know so many things. But what is very common, very common when we are doing this kind of analysis, hydraulic analysis, you consider a certain system, and for that particular system, you are able to define boundaries of that system, so that once you define boundaries, you can be able to determine the inflows into the system and outflows out of the system. An example of a boundary, a watershed. So we are looking at how much water, how much rainfall falls in a particular watershed, and we are looking at outflows from that watershed, how much infiltration from the watershed, how much surface runoff from the watershed. So it is usually very important to define a boundary, so that you can be able now to determine the inflows and outflows into the system. Another very critical aspect that works in systems approach, and you should, if you did not come across it in engineering hydrology 1A, I will state it here. The principle or the laws of conservation of mass and energy have to apply. Basically, it is continuity equation. And what is the continuity equation? Someone who can tell me the continuity equation, because we meet it everywhere. Continuity equation, whether it is mass, whether it is energy, whether it is, whatever, the conservation, law of conservation of mass or continuity equation of whatever. Let us not do for mass, but for whatever kind of a thing. Anyone who can recall? Anyone? So continuity, we are talking about, number one, we know when it comes to mass or matter, you cannot destroy matter. You can only change it from one form to another. But continuity is this. If you have, let's say, for example, and let me give an example using a reservoir. We have a reservoir, assume a reservoir like in a restaurant, and in that reservoir ni mtungi, iko na maji moto, and people come and wash their hands from there, and we have some water flowing into, when the water goes down, we add the water. So at any given time, we are always going to have some storage. We are going to have some storage in that reservoir. So we are going to have some water level in the reservoir. So as people use the water, the level will drop. The level will drop. As people, as we try to replenish the reservoir, we add water by we replenish the reservoir by adding water, and the level in the reservoir rises. So if you get you get inflows into a system and you minus outflows, what you get is a change in storage. So let me start by that, and I want to ask a question so that we can understand that conservation of mass concept. If that is a level of water and we add, we say the inflow into the system I is equals to 10 liters per time, let's say per hour, and I is 10 liters per hour, then the outflow is 20 liters per hour. Inflow is 20, outflow is 10. What is going to happen to our storage? What is going to happen to our storage? And that is why I said, if you can join with volume so that we can be able to have a very nice interactive session. What's going to happen to our volume? Someone. So we have a water level. Is it going to increase? Is it going to decrease?
The level is going to decrease.
Someone has spoken, give me a minute, I just get a cup of hot water. But someone has said it is going to decrease, and that is true because the water coming out of the system is more than the water that is coming from the system. So give me a minute. Yeah, so I'm back. So the level will decrease, that is correct. And the vice versa applies. So that is the conservation of mass. So no, not conservation of mass, but continuity. Conservation is that you cannot destroy it, but matter, but it can only change from one form to another. And when you look at now this example I've given, we have a control volume. That is our reservoir, ile mtungi. And another aspect I have added into this system, we have measured per hour. We have measured per given time. So, we are quantifying all these things within a given time frame. So the hydrologic system, therefore, can be defined as a structure, as a system, where we have inflows per given time, we have outflows per given time, and then we have some operator which lumps together all processes. In this case, we are not going into specifics, but the operator can be a function of so many things. A function of evapotranspiration, a function of land surface, a function of slope, a function of ABC, all those things that affect a function of weather, a function of so many things, all those aspects that affect the various components of the hydrologic cycle. Now, in this hydrologic system, we have all kind of processes operating: physical, chemical, biological. They operate on the media within the system. To produce the outputs. If we look at an example, because I've really explained a lot about this systems concept. If we look at an example, for example, represent the storm rainfall runoff process on a watershed as a hydrologic system. And I already gave it that, the calculation of excess rainfall. That one is usually rainfall runoff, runoff kind of a system. So in that kind of a system, if we look at this example, you have precipitation occurring in a watershed divide, within a watershed, and the boundary is the watershed divide. And inside this process, inside this watershed, you have processes, and the outflow is the stream flow. So basic, very clear. And, like I said, in this level, that is basically what we are going to be looking at. When we look at specifically the hydrologic system model, it is a simplification. So how do we come from a hydrologic system to hydrologic system model? Now, in order to be fair, since we cannot represent the hydrologic framework accurately or comprehensively or detailed every part of it, in hydrology, we usually use models or replicas, not really replicas, but some sort of representation, of the system. And when we convert the hydrologic continuum, the hydrologic system, into a representation, we no longer now are dealing with the system per se, but a system model, mfano yake, a system model. And these models, if I can just sway away a bit from this topic, we have so many hydrologic models that have been developed, which are used to calculate so many aspects. For example, you may find a model that calculates recharge. You find a rainfall runoff model, a rainfall model that is used in river routing, for example, in river engineering, and so forth and so on. A model that estimates evapotranspiration, and so forth and so on. So it is usually basically an approximation of the actual system. So if in such kind of a model, if you assume Q of t, I of t to be the inflows into the system, and Q of t to be the outflows, and then you can calculate Q of t as a function of I of t, or an operator or processes multiplied by the inflows. And we can show that if you follow this derivation or this explanation, you can show that K dq dt, you can express these kind of hydrologic systems, K dq dt plus Q of t is equals to I of t. And this is a differential equation. I don't know which one is it. With this level of equations, when did you do them? When did you do them? Because I cannot even remember how they are solved. It is long time, because at this level, when you get to where we are, some of us, the problems are usually solved for us. But basically, I want you to remember the numerical methods you did, or is it numerical methods? Mulifanya differential equations hizi wakati mgani? What did you call the course? Mathematics 1, 2, 3, or whatever. So basically, in very simple terms, that is a hydrologic system. Do you remember you did base flow separation? Base flow separation, the graphical method and the numerical method. Of base flow separation, we have the aspect of K. The K part, that comes up, which is usually taken as a watershed characteristics, which defines watershed characteristics, if you can recall. But basically, that is all about the systems approach that I wanted to tell you. And the take-home message I wanted us to take from here is, if you have inflows into a system that follows the continuity principle, the outflows can be calculated as a function. Outflows from a system that follows the continuity principle, the outflows can be calculated as a function of inputs. Now, I have some questions here, but basically they are for solving the differential, this differential equation, and I want you people to solve it. I want you people to solve these differential equations. Of course, this course is not about differential equations, but so that you can just remind ourselves that mathematics that we did, and how we can solve. And once you have done it, we can come and share. And discuss the results. Any question about the systems approach? Let us take a break at this point. Then I will still take my roll call at 9 o'clock. So we take a break. When we come back, we are going to come and start off with stream flow hydrograph analysis, part one of it, whereby we introduce the principles behind the unit hydrograph. See you after 10 minutes at about 8:52. Okay, so we continue and we start with the unit hydrograph. I divided the unit hydrograph part into two because first first I wanted us to look a little bit about the background, the theoretical background of it before we go to it. So this first part will just be the theoretical background, introducing the principles, the physical principles behind it, and assumptions and what have and characteristics of it. So we have when we consider generally the hydrology systems model, like I have explained before about the systems concept, change in storage over a period, over a finite period, is a function of inflow and the outflows. So in short, is equals to the inflows minus the outflows. So in short, the storage, the right-hand side, the left-hand side storage is a function of a set of, an inflow function, and is a set of an inflow function and an outflow function. And usually the function is determined by the nature of the hydrologic system being examined. For example, you may just find that F is equals to I minus Q, for example, or F is equals to I plus dI dt minus Q minus dQ dt, up to the first order differentials. And they can go to up to as many derivatives as possible. So that is one, the continuity concept. And I think I already kind of tried to use the wash hands basin in restaurants to try and explain the continuity function of water stored in a reservoir. However, I want to add a little bit further. And I want to ask a question. Assuming that the I don't know which English word to use, but assuming when the water is at this level, the sorry, undo. I will have to use a straight line. The water or the stream of water flows out horizontally due to pressure, and it discharges at that point. Assume it is a smooth line. What do you think will be if the water level drops, say to this part? Will the stream of water go that far? Will it go further, or will it come nearer the tank? I don't know whether I'm clear. Assuming at the level that we have in this image, the stream of water goes almost, let us assume this is 1 meter away from the tank before it starts to drop. If the water level is decreased, will the stream come closer? Will the water fall closer or further away from the tank?
It will fall closer.
It will fall closer. And why? Why? Because the water pressure has dropped. And if it is higher, it will fall further away from the tank. So here, the water stored in the tank has a relationship with the outflow. So the storage, we have seen previously, storage can be written as a function in a hydraulic system, can be written as a function of inflows and outflows into the system using the continuity function. But we come and see again, storage can be written as a function of discharge alone, a function of discharge alone. If we differentiate the storage function represented in equation 2, and we differentiate the storage function um, um, as a function of Q alone, then it is going to be possible for us to be able to equate these two equations. Now, before I go further, any system where storage is a function of discharge is usually called a linear system. And when I talk a linear system, I'm not talking about a situation whereby you have a graph and the relationship is linear. No, a linear system. So we can have a linear model, but here we are talking, a linear model is whereby you can correlate x and y values using a straight line. But a linear system in this case is a system whereby the storage and outflow are correlated. For example, an example of a linear system is the system of base flow. Base flow. Base flow is the groundwater contribution to river flow. And let me explain it a little bit. When after rainfall, infiltration has happened, we have recharge of groundwater if conditions allow. And if you look at groundwater as a reservoir, of course, include imaginary boundaries. So look at groundwater as a reservoir, and you have added recharge through percolation. Water in the groundwater reservoir is going to increase. And because of that, you notice water flow in springs, in streams for those who come from rural areas. The water flow also increases. Why? Because the groundwater reservoir water has increased. As when the rainfall stops and we transition to the dry period like this time, you start noticing a decrease, a consistent decrease in flow in streams. Why? Because the storage in the groundwater is also decreasing, and because of that, the discharge in streams, that base flow contribution in river flow is also decreasing. So there is a direct relationship between groundwater storage and base flow. And because of that, the base flow can always be expressed as a linear model, and it is actually that kind of analogy or concept that enables us to apply the linear reservoir model when separating base flow from river discharge. So a typical example of application of the linear model in a hydrologic system. A second example, when we have rainfall, we have a lot of overland flow. The discharge increases in the river. And as soon as the rainfall stops, the rainfall season stops, or even a storm stops, we start having a decrease in discharge. So even the rainfall runoff model can also be considered to be a linear system. Why? Because storage in the system, because when rainfall flows, it increases storage in the watershed. So when the rainfall falls, storage in the catchment is increased, and when the rainfall stops, the storage now starts to get depleted, and consequently the discharge decreases. inflow into the system. And if you differentiate that previous equation, if you differentiate that equation and substituting that equation in our very first equation, continuity equation, then you come to this equation 4, which is basically equation 4, which is basically the general hydrologic system model. It is a general hydrologic system model. And like I've said, it describes a lumped system because it contains derivatives with respect to time alone, only time and not spatial dimensions. And I have briefly talked about the linear reservoir model. It is a special case of the general hydrologic model where A1 is equals to K, and all other derivatives, all other coefficients are equal to 0. They are equal to 0. And finally, you have the linear reservoir model being written in that format. What we have below is just a rewrite, or trying to simplify these long expressions into a simplified format. For example, m of inflow, the inflow function, and n of d is the outflow function. It is the outflow function. And in this case, it is not solving equation 5, but it is solving equation 6. This is solving equation 6. You get the discharge, because most of the time we're interested with the discharge is a function of the function of inflow divided by the function of outflows. So basically, when we'll be looking at the unit hydrograph, these two concepts, continuity equation, the continuity and storage functions, continuity and storage, we will be basically solving continuity and storage. The functions of linear systems. What are the functions of linear systems? And before we continue now, I want us to take our poll. So that I know whether we are all here ama wengine tumepotea, tumerudi tukalala. For example, like Eddie Kabaya, Emma Grace, Sharon Awino, Tevin Brandon, hao wako tu. Normally I tend to note this kind of name. So Eddie Kabaya, Sharon Awino, Tevin Brandon. Sharon Awino and Tevin Brandon, I can assure you those two just joined to, to you, Mahas, Sharon Awino, and Tevin Brandon. They are just humoring us. Where are we? We are now talking about response functions for linear systems. And what are these functions? The combined inflow and outflow function. And those functions, the MD and the ND, they follow principles. They follow two principles. What are these principles? Which are these principles? One is a principle of proportionality, and the other one is principle of additivity or superposition. What is a principle of proportionality? If a function C f of q is also a solution. The second principle is that of additivity, and that is rather obvious. Principle of additivity or superposition. If you add f of q and f2 of q, if two solutions, f1 of q and f2 of q, of an equation are added, the resulting function f1 of q plus f2 of q is also a solution of the equation. And we are going to apply those two principles to discuss a number of functions that are used in hydrologic systems. And one is the impulse response function. Now, I want to take a break because, when I'm talking about these hydrologic functions and systems, I've been using rainfall runoff. I want to give another example so that we can really understand what we are talking about here. If we have a river, and in this river, we have measured the discharge at this point. We know the amount of water that is at this point A, and then we have water at this point B. If the water getting into point A, and assume there's no seepage from the bed of the river and what have you, so let us imagine only the inflow into the system alone. And the only outflow is outflow from this segment of a river. So any hydrologic, system or any hydrologic part can be represented with a linear model. You can do the watershed rainfall runoff. You can do base flow. You can do even river flow, flow in a river. Imagine any kind of hydrologic representation, any component of the hydrologic cycle. You can represent it as a linear model due to the fact that most of these hydrologic systems, you can express them as linear models. Yeah, I wanted to say that so that we do not only look at this hydrologic system as rainfall runoff only. So the impulse, so normally, before we continue, the solution that we obtain from equation 7 depends on, and if you consider these principles, the solution depends on the input function and initial conditions. Of the values of the output. And in the initial conditions, we take time t to be equal to 0. And if we do not take it as that, it is time t, in this kind of case, when we're doing any calculations, your initial conditions are that period when you start assessing or analyzing your system. So we have the impulse response function, and the impulse response function is basically or rather the response of a linear system can be uniquely characterized by any impulse response function. That is, if a system receives an input of unit amount applied instantaneously. When we talk about instantaneously, we are talking about you cannot measure the time. You are applying it instantaneously. A unit impulse at time tau, the response at a later time t is described by the unit impulse function I is equals to, no, q is equals to u, which is the function of t, by the function u of t minus tau. And tau is the initial time. Tau is the initial time. To explain this better, I want a drummer, and the drummer strikes ile vitu inakaa masahani. So just give it an impulse strike. What happens to the sound? The sound continues until you hear a continuous, impulse until the sound finally fades. That is an example of an impulse input, an impulse input. So you strike, or even strike a mtungi, strike something, and listen how the sound progresses. That is a response. The input was the strike. A sound was created by the strike, and the response was the sound wave propagation. So that is an example. So here we have an impulse, let's say rainfall, and then the response will be the storm hydrograph, for example. But in this case, it is a unit impulse. An example, examples of response to an impulse are a guitar string when it is plucked. Well, I gave that one of a drum. Response of the shock absorber in a car after the wheel passes over a pothole. Now, using the principles of using the principles of additivity or superposition, if you have two impulses, one given at time tau 1 and tau 2, using the principle of superposition of additivity, then you can find that the response is no longer just a single impulse, but you can add those two responses together to get your final result. So in short, if and why is this important? Because when we are having rainfall, we do not only have one drop, but we have continuous rainfall. And because of that, a continuous input can be treated as a sum of infinitesimal impulses. So you can measure rainfall, hourly rainfall, and you can have, the your unit of measure to be 1 hour. So you can measure rainfall from 8 to 9, then rainfall from 9 to 10, from 10 to 11, and so forth and so on. And to get the total output, then you add the response, first, before when you go to adding the response, if you measure the rainfall from 8 to 9, and then you find it is so many units, let's say 5 units, and then from 9 to 10, you measure 2 units. Using the principle of proportionality, 5 times 1 is also a solution. 5 times 1 is also a solution. You can multiply the, what am I trying to say? Using the principle of proportionality, remember, using impulse response functions, you only have a unit instantaneous impulse. So if between 8 and 9, you have 5 units, using principles of proportionality, then you can multiply the 1 with 5. Then in the 9 o'clock to 10 o'clock hour, you multiply, I said, was it 2 times 1 unit? And then in order to get the total response, you add the rainfall in the between the 8 to 9 and then the 9 to 10, so that you can be able to get your output, combined output due to those two impulses. So basically what I'm trying to show is this, only that now here, here you can see here even the unit is 3 units, and here the unit is 2 units. So essentially you will get such kind of a thing. And if you recall, when you look at rainfall hydrographs, for example, not really rainfall, but river discharge, most of the time you'll see some rainfall that is, such kind of things. And then, that is by superposition of impulses, rainfall impulses. It is usually superposition of responses from continuous rainfall impulses at different times. An example, if I of tau, which is the rainfall intensity, if I of tau is the rainfall intensity, and d tau is an infinitesimal time interval in hours, then I tau d tau will be the depth in millimeters of precipitation input to the system during the time interval d tau. Essentially, it is a summation of time, a summation of rainfall within a period d tau. But now in this case, it is in a continuous, it is not discrete, but continuous time frame. And the direct runoff, t minus tau times later, is given by I of t, t of t is an integral from 0 to time t, I of tau u t minus tau d tau. I of t is so many units of rainfall, and u of t minus tau is a unit response. So I of tau is the amount of rainfall, so many units, then u of tau is the response function. If you integrate that, then you get what we call the convolution integral, and this is not, we usually use this as the fundamental equation for solution of a linear system on a continuous time scale. In the figure, where's our figure 3? You'll see later in figure 3, Sorry, it is in the figure that we just saw. It is the response summation process for the convolution integral, because one, in the previous image, here I of tau is 3, I of tau is 3, and in the other case is 2. I of tau is 3, I of tau is 2 in the second impulse. And, this is an example. This is a typical example of application of the convolution integral. Sorry, it is in the next. It should be in the next. You'll see in the next. You'll see in the next figure that will be in part A. It should be. Let's see where it is, because the other one was principle of supervision. So this is the application of the convolution integral. This is application of the convolution integral. This part. So the I of tau d tau is the instantaneous rainfall. And from this instantaneous rainfall, you receive a unit impulse. But remember, since the rain is starting, starting from the time t0, then the response is due to summation of so many instantaneous rainfalls. So back to where we are, that equation is going to be, the convolution equation is going to be very critical in generating the unit, the equations, summarized equations for calculation, convolution, deconvolution equations for calculating the unit hydrograph. Now, in most hydrologic applications, we need solutions at the discrete time intervals, 10 minutes, 1 hour, 1 day, and so forth and so on. In order to handle such kind of input, we have two other functions. We have the step response function and the unit pulse response function. And we will look at those before we end the class today. So the step response function, in this case, you assume that an input goes from 0 to 1 at time 0 instantaneously and continues indefinitely at that rate thereafter. So let me see whether we can see it in somewhere in an image. That should be shown in figure 4. Let me see where figure 4 is. So from time 0, at time 0, the input goes from 0 to 1 and continues infinitely at that rate. So the resulting response is kind of an S shape. The response is an S shape. Remember the pulse response function, we add just an impulse at time 0, but now in the step, it continues infinitely. The impulse starts from 0 to 1 and continues infinitely. So the output function is an S shape. And equated to a g of t function, and is equals to integral from 0 to t u t minus tau d tau. And if you substitute L to be equal to t minus tau, Then the tau is equals to minus dl. The tau is equals to minus dl because the tau is a negative, and the time limit tau minus t becomes L. And the time limit tau minus t becomes L is equals to t minus t minus t minus t is equals to 0. And the time limit tau is equals to 0 becomes L is equals to t minus 0, which is equals to t. And therefore, the g of t is minus t to 0 u of L dl, or g of t is equals to 0 to t u of L dl. Because remember, if this is a minus sign and you change 0, you start from 0 as opposed from t, then that negative value disappears. In short, the function g of t is an integral. It is an integral of the impulse response function. It is an integral. It is the integral of the impulse response function. Then we go the pulse response function. The pulse response function is an input is a response to a unit pulse input. And this is an input of unit amount occurring at duration dt. So in this case, we now start introducing discretization. We start introducing discretization. At this stage, the input is no longer continuous, but we can now specify and say the input is occurring. And the rate is 1 over dt, 1 per time. So 1 millimeter per hour, such kind of a thing. So I of t is 1 dt for 0 is less than tau, and tau is less than dt. So, that impulse unit value is measured between the time 0 and dt. But it is 0 elsewhere. That is, we only have that particular impulse only, and not before, not after. In order to calculate the union, the output from that system, then we apply the two principles that we learned: principles of superposition, principles of proportionality. And let me see if I can get this one in the next.
じ万華鏡車輪眼を開眼しうるものだ。ただしそれには条件がある。最も親しい友を殺すことだ。
イタチ、あんたを殺すためならこの先がどんな闇だろうと俺は突き進む。どんなことがあっても力を手に入れる。
ネジ、おめえの言った通りだ。あいつは今闇の中にいるみてえだ。本気でくれやがって、畜生。
ああ、本気だ。殺すつもりでやった。
もう俺ってばお前にとって仲間でも何でもねえのかよ。俺たち第7班でやってきたことは全部何の意味もなかったのかよ。
いや、無意味じゃない。俺にとってお前は最も親しい友になった。
だったらなんで。
だからこそお前には殺す価値がある。
なんだかわかんねえけど俺を殺そうってのは本気みてえだな、サスケよ。
ひどい。
影分身の術。
Yes, so I'm back. So the first response function, what normally happens in order to calculate it, you get a step response function. So you start with a unit response function, get a step response function, and you lag it by time dt. You lag it by time dt, and if you subtract those two, then you get the response function. So let us see how it goes. So first, by the principle of proportionality, the response to a unit step input of rate 1 dt of 1 dt at the beginning of time 0 is 1 over dt gt multiplied by gt. Gt is the pulse response function. And if you begin a similar unit step input function at a time dt instead of time 0, its response function would be lagged by a time interval dt. And you would have a value at time t is equals to 1 dt gt minus gt of t minus dt. And now using the principle of superposition, the response to a unit function dt is found by subtracting the response to a step unit of rate 1 dt beginning at time dt. So essentially, what we are saying, if you lag this by a time dt, essentially you're just going to move this curve by a time dt. You're just going to move this curve by a time dt, this particular curve here. The S curve, you lag it by a time dt. And the unit pulse response function, h of t, is given by 1 over dt, g of t minus g of t minus g of t minus dt. And this is it, discrete pulse response function. How come it's not working? I have, yeah, it's charging and it's still showing battery low. Okay. So basically this is the discrete pulse response function, and this is the procedure. Sorry, this is the pulse response function, and if you convert it into a discrete function, then this is the discrete pulse response. So this is the continuous pulse response of a pulse input, and this is the discrete. So you start from an impulse response. From the impulse response, you get a step response, you get a continuous pulse response, and then finally you can calculate the discrete pulse response function. So what I'm saying is you start with a unit impulse response, get from that you a step response, continuous step response. You get a response and you can discretize it to get a discrete pulse response function u of n. And this discrete pulse response function is usually actually is the one, it forms the basis. It forms the basis of calculating the unit hydrograph. In an example that I have given, which you can follow, hello, good morning, and Joanne. Yes, did you manage to get an attachment? Not yet. Okay. I'm waiting for a response from Kenha. Once I get it. So the impulse, step, and pulse response functions of a linear reservoir with storage constant Ks is equals to Kq, with a storage constant K, and the storage equation is S is equals to Kq. And I have given the solution there. You can follow to try and get a gist of how the three responses are correlated. Now, further, I have given an example of if K is 3 hours and DT is 2 hours, how the response functions would look like, So we have looked at linear systems as continuous functions, but now we can look at linear systems in discrete time. And I want to leave this at this point so that next time, this was a lot, as an introduction, a lot of this, a lot of that, so that you can look at it, try to internalize, and we'll come and start with linear systems in discrete time. You'll tell me when we can have it. If you have, you create extra time, we can still go through it at any given time. Normally, we would have finished this, but now, but we can always finish it later. So now, I take a final poll and save attendance for the second time. So we have Caroline Kavudha, Joan Akinyi, Muiga, Mutero, Anthony is there. So Caroline Kavudha, Joan Akinyi, Muiga, Mutero. Yeah, those are the, and you will know that they're not following when even when you call their name, they don't respond. We have Caroline Kavudha, Muiga Mutero, and yeah, those two. Okay, so you have a nice day. See you in the next lesson.